Hello, in this video we're going to talk about colligative properties. And this is kind of a longer video because I couldn't think of a good way to break it up into multiple parts. So, here we go. We're talking about colligative properties. And so colligative properties are a number of different things that are grouped together because they only depend on the number of solute particles in solution and not what type you have. So just how much stuff is in solution is what matters, and not whether it's salt or sugar or whatever. And so the colligative properties that we teach in Gen Chem are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So, alright, let's start with vapor pressure lowering. And so this is known as Raoult's law. And the idea here is that your non-volatile solute, it'll lower the vapor pressure of your solution. So we put non-volatile in there because this solute doesn't also have a vapor pressure. When the solute also has a vapor pressure, it's volatile, then we have to treat it differently, which we do in a subsequent video. But for the moment, alright, your solute doesn't contribute to the vapor pressure, and so all it does is it lowers the vapor pressure of the solvent that was in there. And the way to think of this is because the solute molecules, the orange ones in this picture on the right, they decrease the number of solvent molecules that are at the surface because the solute also hangs out at the surface. And so since there's less molecules at the surface, it lowers their tendency to escape from the liquid, and this lowers the vapor pressure. So, okay, put a solute in, vapor pressure goes down. And so there's a way to calculate that. And your solvent will generally do this if it's sufficiently dilute. If you get crazy concentrated, you might have troubles. But so we have on the left here P1, that's the vapor pressure of the solvent above the solution. That's what you're trying to find, the new vapor pressure once you make a solution. And that's related to the mole fraction of solvent. So this is really important, the solvent and not the solute. And then that's multiplied by the vapor pressure of the pure solvent. So if this is water, here's its vapor pressure here, P superscript 0. And then here's the mole fraction of the water. And then you get its new vapor pressure. Now, if you want to know the degree to which it's lowered, then you have to do some subtraction. Here's the original, here's the one you just calculated, and so here's the change in vapor pressure, if that's the way you want to know. So a quick example, the vapor pressure of water is 23.8 torr at some temperature. Now, if you put a non-volatile solute glycerin in, what's the new vapor pressure going to be? So the trick here is that this mole fraction is of the solute, and we want to know mole fraction of the solvent here. And so in order to do that, you need to realize that the solute plus the solvent, their mole fractions, will equal 1. Because it's kind of like a percentage, right? You take all of the pieces, add them together, it equals 100%, or in this case, 1, the decimal. And so, alright, so we can do that. We can take 1 minus the mole fraction of the glycerin and get the mole fraction of the water. And then here's the vapor pressure of the pure water. And so now you take the mole fraction of the water times the vapor pressure of the water, and you get the new vapor pressure of the solution, 18.3 torr. Alright, now we're on to boiling point elevation. So, a solution has a lower vapor pressure than the pure solvent. That's what we just described. Now remember that boiling point is defined as when the vapor pressure reaches the atmospheric pressure. So at a constant atmospheric pressure, if you lower the vapor pressure, you'll have to put in more heat until that vapor pressure reaches the same atmospheric pressure. So then this makes the boiling point go up. A solution has a higher boiling point than the pure solvent. And so maybe it's easier to just look at the picture to describe this. So in blue here is kind of your standard phase diagram. This curve is the vapor pressure of the pure water. And so that's the blue one here. And now when you cross 1 atmosphere, then this is your boiling point. You take this all the way down, boiling point. Okay, but if your vapor pressure is lowered uniformly because you have a solution, now it takes more heat until this curve reaches 1 atmosphere right here. So then the temperature at which this curve reaches 1 atmosphere is your new boiling point. So, and then something similar happens for the freezing point, but it's something that we talk about in a later slide. Alright. So how you calculate the change in boiling point And so here we're calculating just the change, delta T. And so we have a constant here, fancy words, the molal boiling point elevation constant. Impress your friends with that one. And then that's multiplied by the molality. Here, molality comes into play because it doesn't matter about the volume of solution, which molarity tends to care about volume. It matters the amount of solvent you have. So, all right. And now this, unlike the Raoult's law thing we just talked about, this calculates the change in boiling point. So you'll get some number out like 2. And then it's not that your new boiling point is 2, it's that your boiling point went up by 2 degrees. All right, so then down in this table here we have various constants. We're doing boiling point now. The table also has freezing point. And so water's down here. And so for every molal of concentration of solution you have, the boiling point goes up by half a degree. All right, so quick example. So here we have 1 atmosphere, and let's assume it's exactly 1 atmosphere that was prepared, or what's the boiling point of a solution at 1 atmosphere where you have 20 grams of urea in 100 grams of water. So we need to know molality for this. So we have to calculate molality first. So here's moles of urea. Here's molality of urea. If you're curious, urea is a molecule that your body uses to get rid of excess nitrogen. And we first found it as scientists in urine, so it's called urea. All right, so here's the molality of that. Cool. Now we're doing this equation, and we just throw the numbers together as stated. The constant for water, the molality of the solution, and now we have our change in boiling point. And so this change in boiling point is in Kelvin. That's the way the units of the constants are given to you, in this table at least. But that said, we're dealing with a change in temperature. And so remember from before, a change in temperature in Kelvin is the same as saying a change in temperature in Celsius. It's not true if you're talking about absolutes, but when you're talking about changes, that is true. All right, so if you want to find the new boiling point, you have to basically add 1.71, right? So you take your boiling point where it's 100 normally, then you add this change to it, and now your new boiling point is 101.71. When we do these problems, we typically assume the boiling point of water to be exactly 100, just because that makes life easier, and it's not a bad assumption, right? So you can dig into this assumption a little more, hit the link if you're kind of curious, but we don't need to get there at the moment. All right, so now next up is freezing point depression. And so here the solute molecules disturb the equilibrium and tend to lower the freezing point. I don't have a really great explanation of this other than the solute molecules get all up in the way of this solid-liquid equilibrium, and then that tends to lower the freezing point. You need to cool it down even more to really get the solid-liquid equilibrium to work. Okay. Another way to think of this is if you've ever been to a cold climate in the winter, they put salt everywhere. Salt on the roads, salt on the sidewalks. And the reason they do this is that when the snow falls, it will kind of melt a little bit and form a solution with the salt. And then that solution has a much lower freezing point than the pure water. And so at typical temperatures, that'll stay liquid, as opposed to being ice, which can be bad when you're trying to drive. And so eventually, it'll get cold enough that this saltwater solution will freeze. But for most temperatures we reach in this country, that's not a problem. And so they sprinkle salt everywhere, and then the roads stay ice-free. All right, so freezing point depression is a very similar looking equation. You have your delta T, you have a freezing point depression constant, you have the molality. And now one thing that's annoying here is that this will give you a positive number when you do this math. And so then your delta T is equal to not final minus initial, but initial minus final. And that's different to everything else we've done, which is kind of frustrating. So, one thing that maybe would have been better for whoever set up this math is if they would have made all of these constants negative. So then when you do the math, you get a negative delta T, and then that shows that your temperature goes down, your freezing point goes down. That would have been nice, right? But instead it's phrased this way, and I don't feel good just rephrasing it my way, because then you go and do this math outside of the context of my class, and then it's wrong, basically, the way I teach you. So I'm going to teach it to you the way that people do it. And in reality, just calculate the delta T, and then think about it. Wait a minute, is my freezing point going down or up? how does the ice work in winter in Chicago again? Oh yeah, okay, the freezing point's going down. So that means my delta T, well, I need to subtract that from, say, 0 degrees Celsius for water. And now the constant here is different too, right? The freezing point depression constant for water is different than the boiling point elevation constant. So just use the right one. You can imagine on a test that I'll probably give you both constants and see if you can use it. All right, quick example. So here, although, instead of asking what's the freezing point, I'm asking how much glucose do you have to add to drop the freezing point of water by a Celsius. So, and here assume the density of water is 1 gram per mil because I tell you to. Simple enough. All right, so you want to find delta T, and that's a change of 1 Celsius, which is also a change of 1 Kelvin. And so that's the delta T on the left side of your equation. Then you have your freezing point depression constant and your molality, and you multiply those together, and ta-da! All right, so solve for molality. You get a molality of 0.538, 2 sig figs, because 1.0 Celsius. Now we're going to need to do some work to go from molality to amount of glucose. And in doing so, we need to know what mass of water we have, and this is where the density comes in, because 1 gram per mil is, if you multiply both top and bottom by 1,000, is the same as saying 1 kilogram per liter. We have a liter of water. That means we have a kilogram of water. Easy. So, all right, so here's your molality. Then you multiply by the amount of water you have. The kilograms cancel. And so you're left with just moles. And then now you have grams per mole. So you have moles of glucose over here. Then here's moles of glucose. All right, so you can cancel out the moles. And you're left with just grams of glucose. And you have to add 97 grams of glucose to your solution in order to lower the freezing point by a Celsius. Awesome. All right, so now this is the part in the slideshow where I tell you that I've been lying to you for the last, about 10 minutes. So, colligative properties depend on the amount of solute. And, say you put salt in. Well, salt's going to dissociate into these sodium ions and these chloride ions. And so, well, if that salt dissociates, then you're going to have double the effect because you have double the amount of particles in there. So if you make a 0.1 molal solution of sodium chloride, it should have about 0.2 molal of total ions in there. And it's going to do twice the freezing point depression or twice the boiling point elevation. And so to incorporate this into the math, we use this factor. We use this constant. We call it I, named after a scientist, Van Hoff. And the idea here is, okay, so say you put in a mole of solute, a mole of sodium chloride, you're going to have 2 moles of particles. And so then your I is equal to 2. So that's the idea there. Now, to be fair, it's not always quite 2 for sodium chloride and, whatever multiple you would expect. So you have the one that you would expect based on looking at the chemical formula, and then what you observe is often going to be less. These ions tend to transiently pair in solution on very short time frames, and that tends to overall reduce the number of particles globally across your whole solution. And so your I that you actually get is always a little lower than you would expect. And so, for example, when you have sodium chloride, you expect the I to be 2, but the I is actually 1.9. Right? Now, something else we should say, if you have magnesium chloride, that's going to dissociate into a magnesium 2+, and then 2 chloride ions. So I'll even write chloride ion twice. And my arrows somehow always are bad on this. All right, so this is going to make 3 parts. So your expected I is 3. In reality, you get a little less than that because these ions tend to pair together on a short time scale. And so on and so forth. Glucose is a non-electrolyte, so I is equal to 1 all the time. All right. Now we rewrite our formulas to incorporate the Van Hoff factor. So basically we just slide in the letter I right here. And that's fine, right? So these are the equations you'll get on the test. And if you don't have a salt, then your I is equal to 1. You have something that's, a covalent molecule. Now, your textbook uses this thing called colligative molality, where they basically take I and the molality and they multiply them together and make one constant. So then they'd write delta T is equal to KB molality colligative. I don't like that, so I don't use it, but just be aware that that's the way your book does it. All right. So now a little practice about the Hoff factor. What the heck is it? So pause the video, think of this, what it is for each of these samples, and then we'll talk. All right, potassium bromide, you have K+, Br-, that's 2. Ammonium chloride, you're going to have NH4+, and then Cl-, and that makes 2. Now the iron sulfate, you're going to have a lot of particles here, right? So iron is 1 unit, and that's iron 3+. The sulfate is another unit, that's SO4 2-, and you're going to have 2 irons, you're going to have 3 sulfates, for a total of 5 for what you would expect. And then I'll leave this as the pre-quiz question. What is the expected Hoff factor for ethanol? All right, so now let's extend this I to vapor pressures. This is something that I don't typically expect you to do on a test, but I just wanted to point this out that you can also do this with vapor pressures. It's a little more confusing, so that's again why we omit it. But all right, so when you're doing vapor pressure lowering, right, here's your pure solvent, here's your new vapor pressure, and then you're using the mole fraction of the solvent, right, which you might not think would change when you go playing around with your solute, but that's not actually true, because mole fractions add to 1. And so if you, say, have a solute with an effective mole fraction that's greater than what you started with, then it's going to affect this equation down here. So let me say that again. So you have your solute, some mole fraction, but then say it does twice the duty, sodium chloride, say. So then your effective mole fraction is going to double. So then if this number doubles, then this number is going to go down to have them still both equal to 1. So then your mole fraction of your solvent will be lower if you have an electrolyte that dissociates into multiple parts as your solute. Okay. So next up, osmotic pressure. So first let's define this. So osmosis is the selective passage of solvent molecules through some porous membrane, and they go from the dilute solution to the more concentrated one. So in this picture, we have solvent molecules that are over here, these kind of blue dots, right? And it's showing that the solvent molecules, in this case water, you could imagine. I mean, it works with any solvent, but we typically do it with water. They go through this membrane. And now if this membrane is semipermeable, such that water can go through it, but your larger solute molecules, right, your larger solute molecules can't, then that might do something. And so what it does is it tends to increase the volume of the solution, right? So these solvent molecules, the net direction is they travel to the more concentrated solution through this semipermeable membrane. And you can think of it as the reason is that it's trying to maybe lower the concentration of the solution so that solvent solution are kind of have equal potential in a way. You can think of it that way. So the solvent's trying to just equalize things out. Oh, I'm less concentrated, you're more concentrated. Let's try to calm that down and make our differences less. So that's osmotic pressure. So what happens, right, when you do this is, so say you start with this picture. Now over time, your solvent molecules will go through this membrane but not return. And eventually that's going to increase the volume of your solution. And in this kind of simple U-shaped tube setup, that's going to push this higher. And so when this liquid is higher up here, well, gravity is exerting more pressure on it than it would otherwise, right? Gravity is exerting less pressure on this, or less force on this, I should say, not pressure. And, well, so this will kind of continue happening until the extra force from gravity pulling this down equalizes the natural pressure of the system to force this osmosis. Kind of a weird way to say it, right? And so maybe this visual is better. And so I'll start with the picture. So say you put some sort of cap on here and you're pushing on it. Now the amount of force you have to push on this in order to maintain these volumes to be equal when you have this osmosis happening, that's called the osmotic pressure. And so if you have less than this pressure on here, the solution will expand. Now if you put more than the osmotic pressure onto this, it'll push the water backwards through the membrane. That's called reverse osmosis. It's how you purify water, and we'll talk about that in a few minutes. All right, so some definitions here is that if you have isotonic, hypertonic, or hypotonic, they tell you about relative concentrations in regards to osmotic pressure. So isotonic solutions have equal solute concentrations, which then, if you put them in contact with each other through a semipermeable membrane, won't do any sort of, solvent transfer through this membrane. Now, if it's hypertonic, it means your solution is more concentrated than whatever it's put up against. And if it's hypotonic, it means it's less concentrated. Now, what's the effect of this? Let's show that. In a minute, sorry. First, we got to do the equation, then I'll show you the effect of the hyper or hypo isotonic. All right, here's the equation for calculating osmotic pressure. The osmotic pressure gets a capital pi, and P for pressure, that makes sense. Now, I is the Van Hoff factor, so if you have sodium chloride, it's doing twice the amount of colligative property action, then, there's the Van Hoff factor. Now we're in molarity and not molality anymore. And the reason here is because this has to do more with volumes than it has to do with relative composition. And so we need to use molarity, which is moles over liters. The ideal gas constant comes back. I told you it comes back in weird places. Here it is. And then you have temperature. Now, here, the temperature has to be in Kelvin because you're not dealing with a delta T. You're dealing with an absolute temperature that you're multiplying by things. So if you were to put in 298 into here versus putting in 25, you get dramatically different answers. So used Kelvin in that case. All right. So quick little example. Say you have 0.35 molar glucose. And we're going to say that's isotonic with blood at 310 Kelvin. So that means they have the same osmotic pressure. So then what's the osmotic pressure of blood at this temperature? Well, if we calculate the osmotic pressure of our solution, then we'll be there. So let's do that. All right, so osmotic pressure. Since this is glucose solution, I is equal to 1 because it's a non-electrolyte. There we go. Here's your molarity. Great. Now here's your gas constant. So you're going to want to use the one that has a pressure unit in it. You don't want joules per mole Kelvin because we're not dealing with joules, we're dealing with pressure units. And so, okay, so you do that, then everything else in here pretty much cancels. The liters cancel, the moles cancel, the Kelvin cancels with your temperature over here, and you're left with just pressure units, which we call it osmotic pressure. Okay, so this means that you'd have to apply 8.9 atmospheres of pressure to your concentrated solution to have it not absorb any water overall from a pure solvent that's placed in contact through a semipermeable membrane. So what the heck is a semipermeable membrane? Well, we can make these synthetically, and that we use for reverse osmosis. Your body also makes them, and they're called cell membranes. So water can go through your cell membrane fairly easily, but other things can't. Ions, salts, whatever, glucose molecules, they can't go through your cell membrane because your cells are in the business of controlling what comes in or out. And so if you put the cells in salt water, well, the water can go through, so the water is going to go from the less concentrated to the more concentrated area. So if it's higher concentration of salts outside the cells than inside, then water leaves the cells, and your cells tend to dehydrate. This is why you should never drink salt water when you're thirsty, because it tends to pull the water out of your cells and overall dehydrate you. Now, in an isotonic solution, you don't have these problems, right? The kind of passage of water and tendency of water to go to either side of this membrane is equal, and so your cells won't swell and they won't shrink. Now, if you have a hypotonic solution, on the other hand, if you take cells and put them into pure water, well, the water will tend to go into the cell to try to equalize the concentrations, and so this will make your cells swell and eventually rupture. So this is why anybody doing biology in a lab, they always put their cells in some sort of buffer solution that A, maintains the pH, but more importantly, B, maintains the salinity, the amount of ions dissolved, so that you don't have these problems. All right, finally, we're going to talk about reverse osmosis. So if you have your semipermeable membrane, you can make these synthetically so that water can go through and ions can't. If you apply a pressure to the concentrated salt side, And if this pressure is greater than your osmotic pressure, in practice like 2 to 3 times greater, I think, like, just make it greater, then it'll push the solvent molecules, the water, through this membrane, but then the ions or whatever can't go through the membrane. And so this way you can make pure water from salt water. The only problem is, to do this, you need to apply a bunch of pressure here. And, well, that's expensive from an electrical point of view. The equipment you have to use to generate these pressures to kind of force the water through this membrane, that can be expensive from an energy standpoint. And so reverse osmosis, if you're going to take seawater and generate drinking water from it, it's generally more expensive than just catching rainfall and storing it in dams, which is why in the US, where we have a lot of mountains and things, we typically don't use reverse osmosis to generate water. Although now with climate change, we're starting to do that more often because California's in a big drought. So cities like Santa Barbara have a reverse osmosis plant they had to get going again because they're not getting enough rainfall. Whereas countries like Israel that are kind of in a desert climate and don't have mountains to catch a bunch of water, they've been relying on reverse osmosis for years as a way to generate drinking water from the sea. All right, and that's what we have for this video. Thanks for hanging in there through a long video, and I'll see you in class.